Okay, I'm going to show you just a quick example of how you might implement the bias test that we presented in our paper recently on the effects of climate change on Australia's only endemic Pokemon. You could do this kind of in any SDM framework, I think, but just to keep things simple, we're going to use ENMTools. It has a pretty straightforward interface for a lot of the basic functions we're going to need here. Obviously, I'm biased, but there you go. So we're going to load in some rasters for the present day. This is 19 bioclim variables for South America. I'm just going to stack those up. And then I'm going to do the same thing for world clim variables or bioclim variables for a future climate scenario. I think this is 2100. If I remember correctly, I don't remember what the emission scenario and climate model are, but I'm going to stack those up as well. Now we're going to create an ENMTools species object. So ENMTools stores all the data for a species in a single object with a consistent format, which makes it possible to give a fairly uniform interface to a lot of modeling functions. So I'm going to make one for this species. So we create an empty species object. We import some presence points from a CSV file. We give it a name, and then we run this check species function on it, which just essentially reformats everything into the format that ENMTools expects to see. Now we also need to give it a background, so we're going to be using a GAM, which is going to use some background data. So we're essentially going to buffer those occurrence points and treat that as the background. And so there's a function for this in ENMTools called background.buffer. And we're going to run check species again just to be safe. And now we're going to make an interactive plot. So this is just like a leaflet plot of what our species looks like right now. So it's got occurrence points, that's the green dots, and it's got this range raster, that's this buffer we created here, right? So that's cool. Our data looks reasonable. We don't necessarily want to use all 19 of those bioclim variables because there's a lot of multicollinearity there. So we're going to use this function called raster core plot, which basically just takes a stack of rasters, gets a Pearson correlation coefficient for every pairwise set of them, and then it gives you a couple of plots that help you visualize what the relationships between those variables are. So it takes a minute because it's doing a bunch of Pearson correlation coefficients. Okay, there we go. And now we've got a heat map where brighter colors represent combinations of predictors that are highly correlated. We've also got this sort of visualization, which basically does an NMDS on the correlation matrix and plots variable names in this space where proximity in that space is related to how correlated they are. So I'm going to pick bio 1, which is over here. And then we want something far away from that, so bio 15 over here. And then bio 12, which is sort of in the middle. So basically we're just picking a set of these which are pretty far apart. The choices are pretty arbitrary in this case. I'm not really trying to do a lot of model selection here for picking which predictors are important. I'm basically just sort of eyeballing it and saying, okay, these are going to be not that correlated since they're far apart in this space. Okay. So I'm going to subset our raster stacks to be just those layers. And notice here that the future climate layer is 450 by 300, or climate layers. And the present day ones are 1800 by 1200. So our present day data is in a much higher resolution than our future data. So I'm actually just going to resample that present day stuff down to the resolution of the future layers. We're going to be doing some math on models coming out of those layers, so they have to be at the same resolution. And now I'm just going to build a GAM really fast. So ENMTools provides a default formula for a given set of predictors. It's usually a good idea to tweak that and make sure that it actually makes sense and all that. We're just going to go with the default behavior right now because it's not really the point here. So we're going to pass in our species object, our environmental layers. We're going to set aside 20% of our data for testing. And crucially for this purpose, we're going to do 100 RTS reps. RTS is short for Rice and Tersteja. I think I'm pronouncing that right. That's their 2007 paper that essentially showed you could do this geographic randomization to get an estimate of the significance of model fit. That's not what we're doing here. But we're essentially doing the exact same randomization process. So we're just going to essentially adapt that those replicates for a different purpose. So It's going to build an empirical model. It's going to do a bunch of testing and all that sort of stuff. And now it's going to build models for 100 replicates of randomly chosen data points. And so it's just sort of doing it automatically here. Okay, these are just some warnings coming from ggplots. Don't pay too much attention to those. All right, so now we've got this ADLERS-GAM object here, which contains the model, a bunch of plots, and also contains those 100 replicates from that Rice interstitial randomization test. So first off, we're going to project our empirical model onto our future climate layers. And we'll just look at what that looks like real quick. So this is what it says future climate change is going to look like. And if we actually want to look at the using the same kind of plotting, we can actually look at our empirical model that way as well. Let's just do plot. Yeah, so this is what our model says the present distribution of habitat suitability is, and that's what it says the future distribution is. So you can see that it kind of looks like we're going to be losing some currently predicted suitable habitat in the future. So let's actually look at that predicted change. So I'm just going to subtract the future suitability from the present. And now I'll plot that. And so the green areas here are areas where the suitability is expected to increase in the future. And let's see, anything that's not green, essentially, with the way this color ramp is, are places where habitat suitability is expected to decline in the future. So that's interesting. So now we're going to take all of those models. So those are stored inside that ADLERS-GAM object there. We're going to take all those models built for random data points. We're going to project them to the future. We're going to project them onto the present distribution of environmental variables. And we're going to subtract the present prediction from the future to essentially get exactly this kind of map, but for a whole bunch of models built using data that has no signal in it. Right? So just do that with this quick little lapply thing here. This is kind of the only tricky part of doing this test. The rest of it's really pretty straightforward. Okay, so now we've got, if you just want to see here, we've got a whole list of rasters that give the projected difference between the present and future habitat suitability using our empirical study design, but random data. So that's one of them. Here's another one. That's right. So this gives us a distribution of the kind of predictions we might make given our study design if our data had no information in it. So we're just going to stack all those up. And now we can do something like, for instance, calculate the mean predicted change in habitat suitability. So we're just going to take that whole stack of rasters and we're going to take the mean from it. And so look at this. There's areas here where you can see the mean is pretty far from zero. So with uninformative data, you ideally would want a kind of uninformative prediction on average. And yet there's this sort of geographic structure here where this area, even with uninformative data, is predicted on average to be getting more suitable in the future. And this area is on average predicted to be getting less suitable in the future. So that's quite interesting. But that's not all we can do. We can actually take the standard deviation of that stack, which essentially gives us an estimate of how much changes to the data enact changes to the predictions you make in changes of habitat suitability. So here, for instance, these are areas where changes to the input data actually have a pretty large effect on the predicted change in habitat suitability over the next 80 years. Whereas areas like here, changes to the input data don't seem to have much effect at all. So that's interesting to know. So now that we can sort of see where we've got this mean and standard deviation, this distribution of predicted changes, I mean, the obvious question you want to ask is, can I compare that to my empirical predictions? And the answer is yes. You can essentially basically use this function here where we're going for each grid cell, we're getting the 97.5% quantile for the distribution of predictions of habitat suitability change across that stack of rasters, right? So we can plot that. It looks like this. And then we can do the same for the lower quantile, so the 2.5% quantile of predicted changes in habitat suitability across that stack of rasters built from uninformative data. So I'll take just a second here. And that looks like this. And so what we want to say, I think, is that within that 95% confidence interval, those are predictions that are made. That's a sort of range of predictions that are made when our data is uninformative. And so if your empirical prediction falls within that confidence interval, that may be a place where you really want to question whether you should trust what the models are telling you. So basically right now what we're going to do is we're going to find the grid cells where our predicted change from our real data falls within that confidence interval. And so we're doing that here. Right, so the ones here, the little green areas, these are areas where the predicted change in habitat suitability from our real model is indistinguishable from what that prediction would be, statistically speaking, indistinguishable from what that prediction would be if our data contained no information. So these are areas where we might not want to sort of invest a whole lot based on what this model says, because it's a place where the predictions we're making don't seem to be strongly driven by the data. So that's just a kind of quick and dirty demonstration of how you can do this. You can do this with any modeling algorithm. You can do this with GAMs, GLMs, Maxent, whatever. In ENMTools, the procedure is effectively the same. You would basically change one or two words of this to do it with Maxent. So that's pretty straightforward. There's a lot of other stuff you can do with a stack of rasters, though. You could, for instance, you could look at predicted changes in range size, predicted changes in species richness and stuff like that, and get estimates of the bias based on your study design in those sorts of quantities as well. I think that the really cool thing here is not that, there's this one test for bias in this specific thing, but that once you sort of start doing this procedure, you pretty quickly realize you can do a whole bunch of different things with it. And it's really cool that it kind of gives you this ability to say, in geographic space, where are my models more trustworthy and where are they less trustworthy? And so we hope that's going to be really useful to people. Thank you.